Here I'm going to go through a Leaving Cert past paper question on chemical equilibrium. It's one of the shorter questions, a 25-mark question. It's question 11b. So it says to consider the equilibrium represented by the following balanced equation. Write the equilibrium constant Kc expression. Okay, so Kc is the expression which determines what happens to the position of equilibrium for changes in many conditions, and how we write it is it's going to be the concentration of the products, which is in this instance bromine and chlorine, to the power of their stoichiometric equivalent, or to the power essentially of the number in front of them. And there's no number in front of bromine here, so that's 1, and there's 1 chlorine, so that's just going to be bromine concentration times chlorine concentration, all divided by the starting material there, the bromochloride. And because there's 2 equivalents of bromochloride there, B or Cl, I'm going to have to, in a Kc expression, square that. Now, calculate the percentage decomposition into bromine and chlorine of 0.2 moles of bromochloride placed initially in a 5 litre closed container and allowed to reach an equilibrium at 1200 degrees Celsius according to the equation. Take the value of Kc to be 0.22. Okay, so a few things from this. First of all, we know that there's an equal number of moles on both sides of the equation. So there's 2 moles of bromochloride, there's 1 of bromine, and there's 1 of chlorine. So what that equal number of moles on both sides of the reaction means, firstly in terms of pressure, it means that a change in pressure won't affect the position of equilibrium, but also it means that because the reaction is carried out in a container with the same volume, which is 5 litres it told us, we don't need to use concentration in our equilibrium expression because the volumes will just cancel out. For more on that, you can have a look at one of the previous videos, the LC 2020 video. So when we're using Kc, we're going to start here, and I'm going to write moles at the start of, first we've got bromochloride, then we've got bromine, and we've got chlorine. So the moles at the start, you're told that there's 0.2 moles. I'm just going to leave it like that, 0.2. At the beginning, there is no bromine and no chlorine present. Now, next thing we're going to look at is our moles at equilibrium. We don't know the extent at which equilibrium has happened yet. We know Kc, so we don't know how many moles of bromine will have formed in the reaction, or chlorine. So what we can do is we can assume that X moles of bromine is formed, as because it's 1 bromine to 1 chlorine, X moles of chlorine will form. Now, how much bromochloride will have been used up? So the moles of B or Cl is 0.2 minus 2x. Okay, so for concentration, we need to include the volume, okay? So the volume here is 5 litres. I could say that concentration at equal is 0.2 minus 2x over 5, because that's the volume. And then this will be x over 5, and this will be x over 5. But in my Kc expression, because I have to square this term, what's going to happen here is I'm going to have all my denominators are going to cancel. So I'll write that out. I can just show you that. So our Kc here is 0.220. That's equal to x over 5 times x over 5 all divided by 0.2 minus 2x all over 5. Now, in Kc I have to square this concentration, so that's squared. But what you can see is that that 5 are going to cancel with that 5 squared. So I don't need to include the 5. So I'll essentially just rewrite it, and you don't have to write it out like that every time. I'm just doing this to explain it. So our Kc, you don't need to include the volume if there's equal number of moles of both sides of the reaction. So it's going to be x times x over 0.2 minus 2x squared. So transferring this here, we just have 0.220 equals x squared over 0.2 minus 2x squared. But I've got a number on the left of that equation, and I've got a perfect square on the right. So I can literally just take the square root of both sides there. Root 0.220 is equal to x over 0.2 minus 2x. That negates the use of a quadratic equation and our extraneous root. So therefore, 0.2 minus 2x times the square root of 0.220 is equal to x. Now if I can solve that linear equation, then I'll have my answer. So I've got 0.2 times root 0.220, which is actually just 0.0938 minus 2x times root 0.220, which is 0.938 x is equal to x. So therefore, bringing that over to the other side, there, I'm left with 0.0938 is equal to x plus that, which is 1.938x. Divide both sides by 1.938. X equals 0.0938 divided by 1.938, and that's equal to 0.0484. So we're not finished the question yet. That just tells me the number of moles of bromine formed. Now I think we were asked to work out the percentage decomposition into bromine. Okay, so percentage decomposition, if that's the number of moles of Br2 formed, so therefore mole of BrCl used equals twice that, because it's 2x, which equals 0.0968. So percentage decomposition equals 0.0968 divided by our initial amount, which is 0.2 times 100 for percent, which gives me 48.4% decomposition. So a lot of maths involved in that one. So give your answers to the nearest whole number. We've got to do that. That's 48%. Increasing the pressure in the equilibrium mixture intensifies the colour of the mixture but does not change the percentage dissociation of BrCl. So we know that increasing pressure will only change the position of equilibrium if there's a different number of moles on each side of the equation. So increasing pressure will favour the reaction that produces the fewest number of moles, but there's the same number of moles on both sides of the reaction, so therefore we're not going to change the percentage decomposition or dissociation of bromochloride, because there's the same number of moles on both sides of the reaction. Now, increasing the pressure causes the gases to become closer together, so you're essentially changing or reducing the volume there. So if you're reducing the volume, you're just intensifying the colour. So no change in position because of equal number of moles on both sides of the reaction. Yes, a change in colour because you're intensifying the colour because you're reducing the volume.